Hello and welcome to today's lecture on MOS transistors. This is the last lecture on this topic. Today I shall discuss about MOS transistor as a switch. In the last couple of lectures I have discussed how MOS transistor can be fabricated and then basic structure of a MOS transistor. Then I have explained the operation of a MOS transistor with the help of a very simple model known as fluid model. And in my last lecture I have discussed the electrical characteristics of the MOS transistor and I have derived expression for the drain current, and we have seen what are the various parameters on which the drain current depends. Today I shall discuss one very important application of MOS transistor, that is transistor as a switch. And here is the agenda of today's lecture. I shall give a brief introduction about this, and then I shall start with MOS transistor as a switch. Why do you require a MOS transistor as a switch? Then PMOS transistor as a switch, transmission gate, then transmission gate driving a large capacitive load, then I shall consider transmission gate driving a small capacitive load, then I shall summarize what I have discussed. First I shall discuss what is a switch. You may have heard of switch, rather every day you are using switch in your day to day life. What do you really mean by switch? You see, as you get up you have to turn on the light and you use a switch. Electrically it can be represented by this. So, it has got two contacts and you are taking connections. Then these connections can be connected to a say AC supply, and maybe it is in series with a lamp. So, this type of switch is known as toggle switch. That means, if you push it, it will be closed, and whenever you push it on the other side, it will be open. That means, it has got two state, close and open, or you can say close is you can write is as on, and off, you can also write this way. So, this kind of switch, which is known as mechanical switch, you are using in your everyday day to day life to turn on lights, fans, various types of electrical and electronic devices. And as you can see, it has got two states. There is another type of switch which is known as electromechanical. This is you can also call it a relay, is being used in many electronic circuits. What is a relay? It has got a magnet, electromagnet, and switches. There is one middle point. You can see there are three contacts I have shown, and if you pass current, obviously you have to pass DC current because it is a relay, and whenever you pass current through it, this particular middle contactor is attracted to this. That means, these two lines will make contact, and whenever no current is passed through it. So, that means, you have got you can say another switch that can be a in fact electronic switch or some other type of switch, but the current passing through is not very high, but here the current that can be passing through it can be very large. So, this is a relay. As you can see, it has again got three contacts, middle one, then this side, that means whenever this electromagnet is energized, these two lines say S1 and S2 makes contact, and whenever this is not energized, then S1 and S3 makes contact. Here also it has got two state, again on and off. If you are using any, these two can be used for connecting some electronic circuits like say geyser or a or some oven or anything of that kind, which can be controlled electronically. So, this type of switch is very popular. Now, today obviously we shall be discussing about the use of another switch, that is transistor as a switch, that too MOS transistor. Now, whenever we go to use the MOS transistor as a switch, before we discuss that, let us consider another very important aspect, that is characteristics of an ideal switch. So, whenever we say switch, it has some characteristics, ideal, non-ideal. What do you really mean by an ideal switch? Say whenever we close it, then current passes through it, and whatever is the voltage, say this is your V, that is applied across this lamp, you can say. Now, whenever we consider a switch is ideal, when the on resistance is 0. On resistance is 0, that means whenever it is put on, there is no resistance, it does not offer any resistance. So, the whatever voltage you apply, that is applied across the lamp, there is no voltage drop across the switch. So, an ideal switch does not degrade the signal, that is the characteristic. On the other hand, if it is similarly whenever it is off, then resistance is very high, or I mean ideally infinite, but even when if it is very high, it will serve the purpose. That means off resistance would be infinite. So, whenever these two characteristics are satisfied, we call it an ideal switch, and obviously in such a situation whatever signal is connected through the switch will not be degraded or distorted. The signal will reach the load, in this case lamp is the load, without any degradation or distortion. So, this is how we define an ideal switch, and obviously whenever it is non-ideal on resistance, in reality anything will have some finite resistance. That means, whenever it is on, it will have some finite resistance, and whenever it is off, that resistance may be very high, but obviously it will not be infinite. So, that will be the situation of a practical switch. Obviously, we shall see how the MOS transistor behaves in terms of this ideal characteristics. Okay. We have already discussed the we can say MOS transistor characteristic, we have already discussed. We know that there is a variation of drain current as you change the drain voltage, and that is for different gate voltages. So, these are the different gate voltages, and as we know there are three modes. Number one is your cutoff, then this line represents that cutoff region when there is no current passing through it. Then we have seen there is another region, that is your linear, and finally saturation. So, this is your saturation region, we have already discussed that. So, we have to understand whenever we try to use MOS transistor as a switch, where it will operate, in which mode it will operate. at which point it will be operating when it is off or on. Obviously, when it is off, it will be in the cut-off region. That means, MOS transistor is off, it will be cut off, and whenever it is on, it may be in linear or in saturation. On which factor it depends? That means, whenever the MOS transistor is on, it will be either in one of the two states, linear or saturation. On which factor it will depend? It will depend on the voltage across the device. That means, VDS, as you have seen, if VDS, the voltage across it is less than VGS minus VT, then it will be in the linear mode, linear or non-saturated mode. On the other hand, it will be in the saturation mode or saturated mode whenever VDS is greater than VGS minus VT. So, this line, this is the line, this is VDS is equal to VGS minus VT, demarcates the operation between linear region and saturation region. And obviously, whenever you are using it as a switch, you may not have control about the voltage across it, or in other words, it may vary. So, it may operate, the switch may be closed by applying a suitable gate voltage. That means, whenever it is on, it will be made on by applying a gate voltage which is greater than VT, threshold voltage, and off means the gate voltage is, that means VGS is less than VT, and on means VGS is greater than VT, but the operation will depend on the value of the VDS, drain to source voltage. And as we shall see later, whenever the transistor is on, its operation will vary from one mode to another mode. It may switch, it may go from linear to saturation or saturation to linear, and so on. It will depend on the application. Okay. Then, as we already know, for a MOS transistor, resistance is high when the gate voltage is less than the threshold voltage, as I have already told. So, this is in this mode, it is used as a off state of a switch, and for a MOS transistor, resistance is low when the gate voltage is more than the threshold voltage, which I have already mentioned. That means, whenever it is on. Now, let us consider the use of NMOS transistor as a switch. So, NMOS transistor can be represented by this. Here one point you must notice, you are not applying input to the gate. Gate is used to control the operation of the switch. You are applying input to one of the two terminals, source or drain. And in case of a MOS transistor, one very interesting factor is the transistor, I mean the source and drain are perfectly symmetrical. That means, any one of the two terminals can be used as source, the other one can be used as drain, unlike bipolar transistors. In case of bipolar transistors, you cannot really interchange that emitter and collector. That is, emitter, collector and emitter cannot be interchanged, their operation will be different. But in case of a MOS transistor, we have already seen the structure, and from the structural viewpoint, we have seen the physical structure is identical, and as a consequence, later on we shall see same terminal, sometimes it is operating as a source, at other point of time it is operating as a drain, as we go for discussing the operation of a MOS transistor. So, whenever here you are applying, let us assume whenever you apply 0, then whenever this is your VGS, that means, first let us consider when VGS is equal to 0, gate to source voltage is 0. Obviously, here we assumed here this is the source and this is the drain. and this is the gate. VGS is 0. In this particular condition, the transistor is off, that we have already seen, is off. But whenever this transistor is off, what will be the output? Say, suppose you have applied a 0 volt here. Will you get 0 volt at the output? Or say, suppose you apply say plus 5 volt, which we consider to be 1, will you get plus 5 volt? There is a question mark. Why I have put the question mark? The reason for that is, the output is essential, can be considered that there is a capacitor connected to it. Why? This MOS transistor may be connected to other parts of the circuit. Say, suppose it has been connected to an inverter, and as we know, this inverter, they are connected to the base, and they are having capacitance. So, we can say here there will be a load capacitance CL, and obviously CL will hold the charge, and the output will be dependent on whatever was the input before it was turned off. That means, it is acting as a kind of memory. Output does not fully depend on the present input. Just prior to closing of putting the switch off, whatever was the input, that output will be available as you turn it off. And in fact, this property can be used to realize memory devices using MOS transistors. In fact, the dynamic RAM that is realized is they are precisely, it is used in this way. That means, the intrinsic capacitor is used to hold the information. So, that is the reason why here whenever VGS is equal to 0, the transistor is off, but output is not defined. Not defined means it depends on the previous state. So, since it acts as a memory. Now, let us consider the case whenever VGS is equal to VDD. That means, you have applied, instead of 0, you have applied say plus 5 volt VDD supply voltage. In this case, what will happen? In this case, the transistor is on, transistor is on. Now, transistor is on, but what voltage you will get at the output? Will you get 0, or you will get more than 0 or less than 0 depending on the previous state? You see, you are applying plus 5 volt here, and this is 0, and obviously, this transistor will always remain on, I mean irrespective of the output. So, this 0, I mean if this capacitor was, let us assume earlier there was a voltage plus 5 volt here, and it will discharge to 0 eventually. It may take some time because of the finite resistance of the transistor, but in the steady state output will become 0. That means, if V in is 0, then V out is also 0 volt in the steady state. That means, as you can see, the low level voltage, since we are concerned about digital circuits, our input is high or low, 0 or 5 volt. So, this 0 level, low level is passing to the output without any distortion. Whenever the input voltage is say 5 volt, what about V out? Yes. So, output, you see this here 5 volt, here 5 volt. Here you can see the role of these two terminals has reversed. It is no longer source, you can consider it as drain and this as source. So, since this is 5 volt and initially maybe this is 0. So, this transistor is on, but as this capacitor output capacitor charges, gradually it will reach the point where the voltage will be equal to VDD minus VT, which is the threshold voltage of this MOS transistor. At that point this transistor will turn off. So, that means output cannot charge beyond VDD minus VT or say VTN to signify NMOS transistor. So, we can see here the as the input voltage is VDD, you are not getting full output voltage, it is getting degraded and output will be VDD minus VTN. That means, it will be less by the threshold voltage of the MOS transistor, because at that point of time the transistor is turning off. So, here it is plus 5 volt, there it is and then in the gate it is plus 5 volt and here at this point it is VDD minus VT. So, if it rises further the transistor turns off. So, you can see in case of a NMOS transistor you are not getting the full output, it is getting degraded. Okay. What about PMOS? So, let us now consider the PMOS transistor. PMOS transistor. In case of a PMOS transistor, let me draw the diagram of a PMOS transistor. This is a PMOS transistor. Now, in this case whenever you apply 0 volt, then what will be the situation of this? Then the transistor is on. That means, whenever input I mean get VGS is equal to 0 volt, then the transistor is on. The transistor is on. On the other hand, whenever you apply VGS is equal to plus 5 volt, then the transistor is off irrespective of the inputs that you apply. Transistor is off. That means, whenever it is plus 5 volt, then the transistor is off. So, again the transistor behaves like a kind of memory. We have already seen the output cannot be fully defined, it does not fully depend on the present input, it depends on the past input. So, at the point of time when it was switched from 0 to 5 volt, at that point of time whatever was the input, that input will reach the output and it will be retained by the capacitance that is present here. On the other hand, whenever VGS is equal to 0, the transistor is on. Let us see the operation of the MOS transistor when the transistor is on. That means, whenever V in is equal to 0 volt, VGS is equal to 0 volt, at that time what is V output? What is V output? We have assumed that VGS is equal to 0 volt. What will be the output? You see here 0 volt, here it is 0 volt. So, there is no difference, and initially let us assume this was plus 5. So, this source is gate is more negative with respect to the source. So, the transistor is on, but how long it will remain on? As the capacitor charges, it will turn off whenever it will reach VDD minus VTN, VTP, absolute value of the threshold voltage of the MOS transistor, and at that point the transistor will turn off. And so, you can see here the 0 level is not reaching the output properly. that the low level voltage is getting degraded. What about V in is equal to plus 5 volt? So, here instead of 0 we apply plus 5 volt. What will be the output? Let us assume initially it was plus 5 volt. You can see in this particular case this is now acting as a source, this is acting as a drain, and this transistor is always on because gate is more negative with respect to the source plus 5 volt. So, the transistor is always on, that means V output will be equal to plus 5 volt. That means, the high level voltage is reaching without any degradation. So, the characteristic is exactly opposite to that of NMOS transistor. We have seen in case of NMOS transistor, the low level signal was passing without any degradation, high level was degraded. In case of PMOS, just the opposite, the high level is reaching without degradation, low level is getting degraded. Okay. Now, can we now get best of both the worlds? We have seen that the NMOS transistor, neither NMOS transistor nor PMOS transistor behaves like a ideal switch. Either low level is degraded or high level is degraded, depending on the type of transistor you are using. Is there any way by which we can get best of both the worlds? That means, the good features of both the transistors we try to achieve. How can we do that? We can do that by combining two transistors in parallel. So, what we can do? We can have a PMOS transistor in parallel with a NMOS transistor. So, this is a NMOS transistor, then this is a PMOS transistor, and this is your V in and this is your V out. Obviously, to you can turn them off by applying say plus 5 volt and 0. So, in that case it will be both the transistors are off. So, it will behave the output will behave like your NMOS or PMOS transistor. That means, in this particular case output is dependent on the previous value. So, as you can see, we have to apply complementary output inputs to the gates of these two transistors. That means, you have to make them simultaneously on or simultaneously off. So, in this particular case they are off. So, here the output voltage will be dependent on the previous state. Now, to make the switch on, let us apply 5 volt here and 0 volt here. That means, V G S N is equal to plus 5 volt, NMOS transistor we are applying plus 5 volt, and V G S P we are applying 0 volt. That means, the switch is on. In this case, if you apply V in is equal to 0 volt, what will be V output? What will be the output voltage? You can see you have now two transistors in parallel. Okay. The PMOS transistor in this particular case will not pass the 0 voltage, but it will pass through the NMOS transistor. That means, it is 0 volt. So, it is always on. So, output will be 0. That means, a low level signal will pass through the NMOS transistor without any degradation. Similarly, if you apply VDD or plus 5 volt, V output will be again plus 5 volt. A high level signal will pass through the PMOS transistor without any degradation. So, you can see now we are getting a kind of ideal switch in terms of it may not be perfectly ideal, but ideal in terms of that you are getting the low level and high level are passing without any degradation. So, and this particular device is known as transmission gate. which is realized by combining two transistors in parallel, NMOS and PMOS transistors, and applying complementary output complementary inputs to the gates, and by that you can turn the switch on or off. Okay. Now, so far we have considered only the use of PMOS different types of switches to realize, to check whether the logic levels are passing through it out properly or not. Now, we shall study dynamic behavior of the switch, and we shall see whether how the current is shared by these two transistors. Do they share equally, or their current sharing changes as the input and output changes. So, we shall study kind of dynamic behavior, and to do that we shall consider this case where the transmission gate is driving a large capacitive load. That means, you have got a transmission switch, transmission switch PMOS and NMOS in parallel, and let us assume, let us not bother about the off condition, let us assume both the sorry, I have put the opposite way. That means, in this particular case the output will be it will be off. Let us consider the case where we are considering both the transistors are on. So, here you are applying 0 volt and here plus 5 volt, and the transistor is on. In this particular case, what we have done, we have assumed that here you have got a large capacitive load. By large we mean this capacitance value is relatively high compared to the intrinsic capacitances of the devices, which is of the order of femtofarad. Maybe this is of the order of picofarad, not femtofarad. Then we consider it large. Picofarad may not be a very large capacitance, but when we consider in terms of MOS transistors capacitances, then it is large, because the intrinsic capacitances like gate capacitance, source capacitance, these are of the order of femtofarad. So, these are in the range of, let us assume it is several picofarad. Now, what we are doing, we are changing the we are applying a input and suddenly changing it from VDD to 0 to VDD, 0 to VDD. We are changing it from 0 to VDD. Input is instantaneously changed from 0 to VDD. So, you are using you are applying a step input. What will happen at the output? So, since this as we know this both the transistors are on. So, obviously, this assuming that initially this was 0 volt, it will start charging. So, we can say that the output, the capacitance, so this is Vn, Vn had changed from say so let us assume this is the time, this is t is equal to 0. At this point it has changed from 0 to 1. What about V output? What will happen? Obviously, at this point the output, this is your V out, and in this axis it is t. So, initially the voltage was 0. So, it will charge, it will charge, the capacitor will charge, and output will gradually build up, and it will go from 0 to VDD eventually. So, 0 to VDD. So, at the output goes from 0 volt to VDD during this period of time. Obviously, this time will be dependent on the on resistances of these transistors, which are not 0, If the on resistances were 0, it would have charged instantaneously, but this will not happen because the on resistances are not really 0, they have finite on resistances, and the capacitor will gradually charge from 0 to VDD, and during this period we shall see the condition of these transistors, how they change with time from this 0 to say T 1. This is the time during which the output is charging from 0 to VDD. Okay. So, initially what will be the condition of these two states? We can divide the operation in 3 regions. Region 1, region 2 and region 3. How we shall define the 3 regions? Say initially what will be their states? You can see here this here it is VDD and here it is 0 volt. So, what will be the condition of these two transistors? In which state they will be? What will be the mode? Will they be in off state, will they be in linear state, or will they be in saturation state? You can see here, since this is 0, here initially this is VDD at time t, and output this V out is 0 and input is VDD. So, in this particular case both the transistors will be on. It will be on, why? Because this is 0 and this is VDD. So, this is acting as a source, this is acting as a source, and this is acting as a drain for the PMOS transistor. So, this transistor will be on, and since large voltage is applied across it, the transistor will be in the saturation mode. Similarly, for this transistor, this output is 0. So, this can be considered as source, this can be considered as drain, and this is gate. So, again this transistor will be on, and since the voltage difference is VDD, again the transistors will be, this transistor will be in saturation. That means, we can say both the transistors are in saturation. Both PMOS and NMOS transistors are in saturation. When their state will change? When the condition of the transistors will change? You can see, so far as the PMOS transistor is considered 0 volt and VDD fixed. So, this transistor will always remain on. However, it may switch from saturation to linear. A point will reach when this is equal to VTP, absolute value of VTP. That means, the voltage is charging and it reaches the absolute value of VTP. At that point of time, the PMOS transistor will switch from saturation to linear mode. That means, in this case PMOS in linear. What about NMOS? NMOS case, we can see the voltage here is VDD, this voltage is VDD. In this particular case, what is happening? The voltage, the transistor is in saturation, but what will happen? The NMOS, it will remain in saturation because the gate voltage and drain voltage both are changing, we can say. You can see this is remaining same, drain to source, this voltage is changing, and gate to source both this is also changing because it is rising. So, NMOS will remain in saturation. And what about region 3? Region 3 will occur when the voltage is at this point which is equal to VDD minus VTN. Whenever it reaches this point, then what will happen, this transistor will turn off, because here it is VDD minus VT, this is VDD and this is VDD. So, this transistor, the source to drain voltage will become less than VT at beyond this point. So, this NMOS transistor will turn off, that means PMOS will continue to function in linear mode and NMOS will turn off. So, we can see as the capacitor charges, we have assumed that it is linearly charging, but we shall see whether it is linearly charged or not, because we can see here the transistor conditions are changing. In the region 1 both are in saturation, obviously the current drive will be high whenever this is the case. Then as it goes to region 2, PMOS is going to linear mode and NMOS remains in saturation, current drive will reduce, and when in the region 3 PMOS in linear mode and NMOS is off. So, current drive will be less. That means, the current here we have assumed it charging at constant current, but that is not true. That means, the current is changing as the capacitor is gradually charging. So, it will be maximum in the initial part, that this first part 0 to absolute value of VTP, and in this it will be moderate and it will be low. Okay. So, but we have identified 3 regions of operation whenever you drive a large capacitive load. And how the current changes. Now, we shall discuss how the current changes. We can derive the expression for current. We have all in the last lecture we have discussed the saturation current, non-saturation current. I mean, when the transistor is non-saturated mode, what is the expression for current, and in the saturation mode, what is the expression of current, that we have expressed in terms of the drain voltage, gate to source voltage, and we know the drain voltage and gate to source voltages, various voltages are known to us, because you can see here the output value voltage is changing. So, for this particular transistor the gate to source voltage is changing, because it is equal to VDD minus V output. On the other hand, in this case the gate voltage is remaining same, however, drain to source voltage is changing, and accordingly you can derive expression for current in region 1, in region 2 and in region 3, because we know the expression for current for linear and linear mode and saturation mode. Okay. So, let us consider, let me redraw it. So, this is the time and 3 different regions we have already divided. Now, consider the current I. So, let us, we have already divided into 3 parts starting from here. So, in the first part the what happens to the this particular PMOS transistor? PMOS transistors is remaining in saturation in region 1 and region 2, in region 3 it is going to linear mode. So, the characteristic for the PMOS transistor will be somewhat like this. This is your VD. That means, in these 2 regions, region 1 and region 2, this is the IDSP. The PMOS transistor current is depicted by this. It is in saturation mode in region 1 and region 2. In the region 3, it is in the linear mode, as you can see. What about the NMOS transistor? For NMOS transistor, we have seen it is in saturation in region 1 and region 2, but in region 3 it is turning off. but although this transistor is in saturation, but its gate to source voltage is changing. Gate to source voltage, when the transistor is in saturation and gate to source voltage changes, what happens? We have seen that the drain current changes following square law. It is not linear. At the gate voltage is reduced, the that I have, although I have drawn it equally spaced, but that we have seen that expression is dependent on VGS minus VT whole square. So, it will reduce following a square law. So, that means, here what will happen, assuming that initially it is current is same. So, it will be somewhat like this. It will reduce not linearly, but it will reduce quadratically. So, this is your I d s n. So, I have not really drawn I mean written the expression for currents, but I have simply drawn the waveforms. Current expression you can write, because you know the gate voltage, you know the drain voltage, and you can write the expression for drain current for PMOS transistor and NMOS transistor. Now, the current that will be charging the capacitor is connected here, sorry, the capacitor that will be charging, obviously this one will be having the sum of these currents will flow through the capacitor. So, what will be the value? It will be double here. So, that means it will be somewhat like this. If we sum up these two, this part is constant. So, it will be nature, for this part nature will be somewhat similar to this, because you have summing up, then it will be like this. So, you can see it is not really constant. So, that means during this period, as I mentioned earlier, current will be maximum in this range, but it is reducing, then it will further reduce, then it will become the linear mode current of the PMOS transistor. So, this will be the current that will be passing through the device. Okay. So, this is the current that will be charging the capacitor, and it will charge to 0 to VDD. Okay. What about the here the same thing is region 1, region 2 and region 3 I have already explained, and the type of curve that we will get I have already drawn, and as you can see it is same what I have drawn on the piece of paper. Now, let us consider the resistance. So, resistance, as you can see, this is the current. How the resistance will vary? Resistance expression you can get by dividing the voltage across the device by the current, and you can see the NMOS transistor will turn off here. So, it is in linear mode. So, resistance is, you can see, gradually increasing, current is reducing, resistance is increasing, and it will become infinite or very high at this point when it switches from region 2 to region 3. On the other hand, for the PMOS transistor, it is in saturation mode, but current will keep on decreasing because of the reduction in the value of the gate voltage. So, gate voltage is reducing. So, I mean drain voltage will be reducing, and the RP resistance value will be like this. Current will remain same, drain voltage is reducing and resistance is reducing, and it will be constant, because in the linear mode resistance will remain same. So, you can see we can combine these two together, because they are in parallel, these two devices are in parallel. So, sum of these two parallel combination of these resistors will be like this. So, you can see here the current that will be passing through the resistor is like this, more or less constant. Okay. We can now consider another situation where the input is, earlier we have seen input is changing from low to high, now input is suddenly changed from high to low. So, in this case output will gradually discharge, assuming that initially it will be high and then gradually discharge to 0. So, it will gradually reduce from 0 to VDD to 0. So, as it goes from VDD to 0, what will be the state of these 3 transistors? Again you will see the operation will be can be divided by dividing the operation, I mean the entire region into 3 parts. In the region 1, it will be equal, the V output will be equal to, I mean both NMOS and PMOS transistors are in saturation. Initially both of them will be in saturation, because you know the output here it is VDD and here it is 0. So, let me draw it so that I can explain it in a little better way. So, this is your PMOS transistor, this is your NMOS transistor. So, initially here it is 0 volt, you have applied 0 volt, you have applied VDD, both the transistors are on, and initially here it is VDD. Then what will be the condition? So, you can see this transistor now will be always on, NMOS transistors will be always on, contrary to PMOS transistor that was always on in the previous case. And this transistor will be on also on initially, because here it is VDD. So, this is the source, this is the drain, and this is the gate of PMOS transistor. On the other hand, this is the source, this is the gate, and this is the drain of this NMOS transistor. So, initially both are in saturation as it is written here. But as the output voltage, so this is connected to VDD and this is connected to 0. So, as the voltage reduces to VDD minus VT, then this transistor switches from saturation to linear mode. Of course, this transistor remains in saturation. So, because you know that gate to source voltage and drain to source voltage is, you know, the difference is now VDD minus VT. So, this goes to saturation to linear mode as it is written here, NMOS in linear region and PMOS in saturation region, when the output voltage is going from VDD to minus VTP. And finally, in the region 3, when the output is VDD minus VTP, NMOS in linear region, it remains in linear region, and PMOS in cutoff region. So, you can see the PMOS continues to operate, continues to remain on, but PMOS transistor turns off. So, as it is shown in this diagram, this is how it happens. Region 1, V output is less than VTN. So, the NMOS transistors remains in saturation for both region 1 and region 2, but the PMOS transistor turns off here and at this point when the output is VDD minus VTP. And so, we can see the operation is somewhat similar, but the role of the PMOS and NMOS transistor changes in this particular case. Okay. And accordingly, we have just like the previous case, current is drawn. This is the PMOS transistor current, this is the NMOS transistor current, and this is the sum of the two currents. And similarly, the resistance also will be somewhat similar. Only difference is the role of NMOS and PMOS transistors. As you can see, the resistance is somewhat identical to the previous case. Now, let us consider another very interesting case when the output is a small capacitance. You have connected a small capacitance to the output of the transmission gate. So, whenever the output capacitance is small, what will happen? As the input changes from 0 to VDD, since the capacitance is small, it will charge very quickly. So, if it is charged slowly, then the output will follow the input with a small difference. That means, if the in this particular case, if this is the input, if this is V in, output will be, this is time and this is V output. So, this it will be somewhat like this. That means, the output will follow the curve, follow the input voltage, but with a difference. And in this particular case, again you can divide the operation into 3 regions as the input changes from 0 to VDD. Region 1, V in is less than VTN, NMOS in non-saturated, PMOS in cutoff. One interesting point is here, you can see voltage difference is always very small between the input and output, and as a consequence the transistors will never be in saturation mode, because you require a high voltage across it for the transistors to remain in saturation mode. That is why initially NMOS in non-saturated, PMOS is cut off. Then as you go to region 2, then NMOS in non-saturated and PMOS is non-saturated, and as you go to region 3, NMOS is cut off and PMOS is non-saturated, as it is shown here. So, VTN to VTP, absolute value of VDD actually it will be VTP and this is your VDD. So, you can see here the current for the 2 transistors are shown here. For the NMOS transistors, current reduces quadratically. Here it is shown, I mean linear curve, but it will be a quadratic line. So, it will reduce quadratically. For NMOS PMOS transistor, the current will pick up quadratically up to this region. So, it will turn on here. Initially we have seen it was off. So, in the first part it was off, then it will build up quadratically, because the gate voltage is increasing. On the other hand, for NMOS transistor it will decrease quadratically, because gate voltage is reducing gradually, because input is linearly increasing. So, this will be the current that will be passing. Similarly, you can find out the equivalent resistances. This is the resistance of the PMOS transistor. Initially it will be very high, because it was off in this region, then it will reduce gradually. For NMOS transistors, initially it will be low, then it will increase and it will become very high or infinite as it reaches goes from region 2 to region 3, and the current will be the parallel value of resistance is more or less same, as you can see, it remains constant. So, we can summarize what we have discussed today. We have seen MOS transistors can be used as switches, of course, with some limitations, and transmission gate provides near optimal switch, as you have seen it is closer to ideal. Then we have seen in case of transmission gate, 2 parallel transistors supply current to the load, and behavior of transmission gate driving a large capacitive load has been discussed in detail. Behavior of a transmission gate driving a small capacitive load, it will be small, here is a typo, small capacitive load has been discussed in detail. So, with this we have come to the end of today's lecture and our discussion on MOS transistors. And as we are following the bottom up approach, in the next class we shall discuss the operation of MOS inverters. So, we shall start discussing on MOS inverters starting from next class. Thank you.